This video introduces you to merge sort, which is a popular sorting algorithm based on the divide and conquer technique. For those of you who do not know what divide and conquer is, it is basically an algorithmic designing paradigm or a basically way to solve a problem by breaking down the problem into smaller components. So we try to solve the problem by breaking down into smaller components and build the solution from bottom up. So merge sort is based on this divide and conquer philosophy, and it has three steps where you basically divide the array or the collection that you have initially into smaller chunks, which is you initially divide this array into two equal halves, and then you apply merge sort on these two halves. So in the divide step, we repeatedly do this, which is now we are going to apply merge sort on these two sub arrays till we have sub arrays that have size either 0 or 1. Now in the conquer step, what we do is we see whether we have solved the problem or not. So initially, like when we have like smaller sub arrays that have size 1, we know they have just like one number in it. So in that case, they are already sorted. So we know that we have solved the problem. In the final stage, what we do is we combine the results, which is once we have divided into individual components in our array or in collection, what we do is we compare like these two elements, and now we combine our results to merge the two lists which are already sorted. So you repeat this till you merge all the elements in one of the arrays. So let's take a quick example of merge sort, and then we are going to see like the pseudocode, as well as we are going to determine what's the time complexity of this algorithm. So initially we have this array that has these numbers. In merge sort, what you're going to do is you're going to break this into two arrays of size. Let's say in this case, the total size of our initial array is 6. So if we divide 6 by 2, it's 3. And get like a nice even result. So we are going to divide it into two chunks. One will be 6, 5, and 22. And another one will be 10, 9, and 1. So how can we divide this is, let's say if our function is called merge sort, we can just call merge sort on the left half, which is we can pass our array with the value 0 comma mid, which is the size of the array divided by 2. And then we can call merge sort on the right half, which is technically equal to ARR comma mid plus 1 and the end, which we already have access to. So in the first kind of like pass or in the dividing stage, what we are basically doing is we have broken down this array into two small halves which are of equal size. Now we are going to call merge sort on these two halves. So we are going to recursively call merge sort on the left half. So again, like since the size of this left half is still greater than 1, we are going to calculate the middle, or the middle, which is the sum of which is basically size divided by 2 of the array. So in this case it will be 3 divided by 2, which is 1.5. So you can stick to either one of them, which is you can take either the floor of this number or the ceil of this number. Let's say if we stick to taking the floor of this number, then we are going to call merge sort on this left half, which is 6. And then we are going to call merge sort on the right half, which will be 5 and 22. Similarly, we are going to call merge sort on the left half for this array. So in this case, it's going to be 10 and 9 and 1. So you can see in the next iteration, we'll have something like this. Next, we know like this array is already having one element, so we stop right here. But now this subarray still has two elements, so we are going to call merge sort on its left half and merge sort on its right half. So we'll have like 5 and 22. And this will be 10. And then these will be like two different elements, 9 and 1. So at this stage, what we have now is all the arrays have just size equal to 1 or 0. So now what we are going to do is we are now done with this divide stage, and now we are going to go to the conquer stage. So in the conquer stage, we are trying to find out like is our smaller elements already sorted or not. So in this case, we know if the array has just one element, we know each of these arrays are already sorted. Okay, so in this case, in the conquer stage, these numbers are sorted, and now what we are going to do is we are going to merge them to again form lists which are now sorted. But in this case, we are just comparing one number with another number, and we are going to merge these into two lists. But the property here is that the each of the lists that we have, or each of these arrays that we are going to combine, will already be sorted. So in this case, first we are going to like, since 6 has no other child on the right, so it will not be merged now. But 5 and 22 are going to be merged into an array which has size 2. 10 doesn't have children, so it's not going to be merged right now. 9 and 1 have are basically siblings here. So in this case, they are going to be merged into an array. In this case, now the values will be 1 and 9. So at this stage, what we are going to have is we are going to have these values in the array such that we have 6, 5, 22 in another array, 10 in another one, and then 1 and 9 in another one. Next, we are going to combine these two and these two because they are a part of our recursive call uh, from the same parent. So how this is going to work is, let's say if we have to merge like these two lists, and we know like these two are already sorted, so we can create a new array of size 3. We have pointers to the first elements of these two sub arrays. We are going to compare each one of them. The smaller one we are going to put into this array or place that into the array. Next, we are going to move the pointer to the next element. We again see which is the smallest one. So we put that into the array and move it to the next one. Now it's like null, or we do not have any element. So we can add this number to the end of the list. Similarly, we'll add these numbers or merge these numbers into a list on the right hand side of our recursion. So in this case, 1 is the smallest one. So first we are going to add 1 to the array. Next, we are going to move this pointer to here. 9 and 10 will be compared. 9 was smaller, so we are going to insert 9. And then we are going to insert, like we have already reached the end of the list, so we can just insert this 10 at the end of the list. So at the end of this iteration, we'll have like two lists, one based on our left recursion to this recursive call, and the second one is based on uh, this recursive call, which is 1, 9, and 10. Finally, we are going to combine these two lists into one list of size 6. So again, we'll have pointers to both of these lists, and we know that this list is already sorted, and we also know this list is already sorted. So the key idea here is this merge step, which is at every step we are doing merge, and we can do these merges in O of n time. And the reason why we can do them is based on the property of the list that these two lists are already sorted. So what we are basically doing is we are adding like 1 here. Now we are moving the pointer to 9. So we are comparing 9 and 5. So in this case, 5 will be added and we'll move this pointer. So 6 is smaller. We'll add 6, move the pointer to here. We'll add 9, move the pointer to here. We'll add 10. We are done. So whatever is there in this list can be added at the end of this list. So finally, we can see that we have sorted all our numbers based on this method. Now, one thing you have to note here is that like a lot of comparisons will not be made if we know by this property that the lists are already sorted. So what I mean by that is, like, let's say if we take some other example that has some numbers that like one of the lists have like 1, 2, 3, 4, and let's say this has like 10,000 elements, and another list has 10,001 to, let's say, 100,000 or 20,000 values. So if I were to merge these two lists, or if I were to sort these in merge sort, what I can do is I'm going to repeatedly move this pointer to the next one till I reach the end of this. So in this case, like if I combine this into a new list that has size 20,000, I first insert like 1, 2, 3, 4 in a linear array or something like that, in a linear for loop. Next, I can just add this list to the end because I've never moved this pointer and I've reached the end of the first list. So I can just append this list to the back. Now, this is saving a lot of time because, like in other sorts that we have seen so far, what we were doing is we were comparing like each element with every other, which is one was being compared to, let's say, 15,000, 16,000, and so on. But in this case, what we can see is we have already reduced our solution space by half because we have just compared it with the first element. And based on the property that this right half this right half is already sorted, we do not have to compare like one with the other values. So that's why we are saving a lot of execution time. So the key idea here is, we once we call the divide step, which is when once we call recursively the left hand side or the right hand side of the sort, when we implement this can be neatly solved using a recursion, such that like when you are recursively calling the functions, when you are at this stage, which is once you are at this stage, you will actually solve all these different components, which is all of this will be solved in this level of the recursion. Similarly, all this work that your algorithm is doing will be executed at this level. And then for the last one, it will be executed at the first level of recursion. So we are going to very soon see the code for this, and we are going to talk again about this. So let's talk about like what would be the time complexity of this code. So when we are breaking down our problem by calling the divide step, what we are basically doing is we are calling merge sort, which is our name of the function, on our array with starting from like 0 to length. Like that should be our initial call to the merge sort function. Next time, what we are going to do is in this function, we are going to check if our array dot size is less than like 2, because if it is less than 2 we don't have to do anything, which is the list is already sorted. If it is less than 2 we just like stop. Otherwise we are going to call merge sort, which is like I'm just abbreviating this function to ms, on array comma 0 comma uh, length minus 0 divided by 2, and you can take the floor of this, and then the other one from length minus 0 divided by 2 plus 1 comma length. So we are basically calling merge sort on these left and right halves, and these merge sorts have complexity O of 1 because we are just recursively calling the function. We are still not doing any amount of work. So let's just delete this, and then I'm going to discuss the other parts of the execution, why they are what they seem. So in this case, at every level, like once we reach this entire recursive level such that we have just one element, then our recursion is going to go back up. And once it goes back up, we are going to go into the combined stage. Now in the combined stage, what we saw was if we have like two different arrays, like let's say if we have these two arrays, which are of size 1, we are going to combine them, which is we are going to merge them. So merge is going to have complexity O of n, because if we have two sorted lists, we can merge them in O of n times. So that is the key here, which is if we have like two lists or two arrays, we can combine them in O of n, and as they grow bigger, like even if like here let's say there are two lists, we can sort two sorted lists, which is we can merge these two sorted lists into one list by in O of n execution time. Next, what we are going to see is like how many times are we going to combine this list. So when we talk about how many times are we going to combine this list, which is how many times are we combining our arrays, this is dependent on how many recursive calls we have. So let's say if we repeatedly call merge sort, we are basically dividing our first problem that we have into halves at every step. So that's why the total number of steps or the total height of this entire recursive tree is going to be at most log 2n. Because in a way, if we have, let's say, 100 elements, what we can do is if we divide that by 2, at each step we are dividing the problem into halves. So in roughly around 8 steps, because if we take the log of 100, that is somewhere around like 2 to the power 7, like it's less than 2 to the power 7, which is log 2 to the power 7, which is again like roughly equal to 7. So in roughly like 7 steps of recursion, we will get the list sorted, which is we'll get the list combined. So the total number of times the list will be combined is proportional to the log of the problem, which is the log of the initial problem, because we are dividing the problem into half in each step. So next we are going to see in the next video, we are going to see the pseudocode for this problem. But the general idea of the merge sort is that you can solve the sorting problem in O of n log n time, which is log linear. Like this is an example of log linear, and it's a much better improvement compared to all the other sorts we have seen. And actually, theoretically, this has been proven that you cannot solve any sorting problem if you do not have any characteristics of input in less than O n log n time. Now, the issue with merge sort is like when you're combining these smaller sub arrays into a new array, you have to initialize a new array that is going to store the combination of the list. So that is one huge problem. So that's why we require about O of n's new space to solve the combination of the list. So it requires like additional memory. It's an open problem to solve this in place, like nobody has solved it yet, which is like in the earlier bubble sort selection sort, we saw that we were sorting the elements in place, but right now it's an open problem. I think there's $1 million prize on this, so if you solve it you'll get $1 million. There are some movements going on to solve it, like there has been some advancements, but they are beyond the scope of the course because they are too tricky, so we are not going to cover that. But the key idea is you break down the problem into smaller halves and you recursively solve the smaller problem, and then you build up the solution by combining the recursive smaller parts, which is in this case we were combining these. So since each of the combination stage requires O n log n times, and we are building this back up, which is the total number of recursive calls is log n, because we are dividing the problem by 2 at every recursive call. That's why the total complexity is O n log n. In the next video, we are going to see the pseudocode for merge sort, and we are going to also discuss the code for merge sort as well as do like a small example on how the code will actually look like in the compiler. Thank you.